We clearly need an alternate and more sustainable building solution, one that allows us to live gracefully with nature. If you look at the natural world, you'll find innovative design solutions which have been fine-tuned over billions of years of evolution. Biomimicry is the application of natural forms and systems to the built environment. These designs can optimize resources, allowing for a reduction in building materials. They can repurpose waste and create closed-loop cycles. And finally, they can shift us away from our reliance on fossil fuels towards natural and renewable energy resources. Let's look at how biomimicry can be applied to building materials to reduce waste. Concrete manufacturing is responsible for approximately 5% of the world's total CO2 emissions. For every ton of concrete produced, 1 ton of CO2 is released into the atmosphere. To solve this issue, one company asked, what if concrete could remove rather than release CO2? So they looked to the natural world to study how some living creatures extract carbon from their environments to produce strong structures. The best source of inspiration turned out to be coral reefs. Coral reefs are the exoskeletons of tiny soft-bodied polyps. These polyps build their exoskeletons by extracting carbonate ions from the ocean and converting them into a solid state. This process also benefits the environment by balancing out the pH of the surrounding waters. Using coral as their inspiration, the company produced a line of concrete called Calera, which recaptures CO2 and calcium from industrial waste emissions and converts it into a solid form of calcium carbonate to produce concrete. This creates a closed loop and prevents unnecessary waste. Our skin naturally helps to regulate our internal body temperature. When we feel cold, goosebumps raise the hairs on our body to increase a layer of insulation to help keep us warm. When we are too hot, our pores expand and we sweat to release heat and cool ourselves. Biologist Doris Sun Kim used skin as an inspiration to create a building facade out of thermobimetals. Thermobimetals consist of 2 different metals which expand when exposed to sunlight, causing the facade to curl. The curling of the thermobimetals can be used to open pore-like structures, thus increasing ventilation to an interior. Or they can be applied in between double glazing, where the curling can increase shade and reduce solar heat gain. This system requires no energy input and can reduce the need for energy-intensive air conditioning systems.
The Eastgate Center in Zimbabwe was modeled after a termite mound. The design allows the building to passively cool its interiors using stack effect, thereby eliminating the need for energy-taxing air conditioning systems. In nature, termites control the interior temperature by building large mounds from soil, which encompass a network of tunnels. Termites work to expel the nest's excess gases to the surface. Cool air funnels into the sides of the mound and circulates up a central channel through the middle using convection. Similarly, the Eastgate Center houses 2 towers separated by an atrium. The air is drawn from the interior atrium, which gets vented through the floors and structure until it escapes through chimneys on the roof. This iconic skyscraper in London, called the Swiss Re Tower, ventilates air in a similar way as a sea sponge. The Venus flower basket sea sponge found deep in the ocean inspired the 600-foot blast structure. The sponge creates a complex exoskeleton of silica fibers, providing it with effective strength to protect from ocean currents. The cylindrical skin formed helps filtration of nutrients and water for the organism through spaces in the framework. In a similar way, the tower funnels wind from the exterior into the structure and channels it upwards throughout the structure's offices and spaces. The building's floors are staggered around a core, serving as a cavity for ventilation, creating a 40% decrease in heating and cooling consumption.
In 1998, Grimshaw Architects built one of the world's largest greenhouses. The large geodesic domes consist of hexagons and pentagons arranged in 2 alternating spirals, based on a natural phenomenon called phyllotaxis. Phyllotaxis refers to the growth patterns in plants, specifically the positioning of new leaves around a stem. This pattern just so happens to follow the Fibonacci sequence. These Fibonacci spirals are found throughout nature. The geodesic pattern for the dome was advantageous because it allowed the structure to have the lightest weight, the greatest strength, and maximum surface area on a curve. The alignment of hexagons based on natural spirals was so pragmatic and strong that it allowed the builders to reduce the structural building materials by more than half. It is evident that natural forms and design systems can be applied to buildings to reduce building materials, optimize natural and renewable energy resources, and create closed-loop cycles where wastes are repurposed. Nature's solutions provide limitless opportunities for a sustainable future.